All right, here we are. These are the notes for lesson 9. That's unit 3, lesson 9. And the main concept here is analyzing graphs. Analyzing graphs. This is one of my favorite topics in Algebra 2. It's the one topic that when I started teaching Algebra 2, I was like, wow, this is actually super powerful. This is about the connection between algebra and graphing, between the three rules of algebra: solving equations and graphing. It shows you how the two things are related and how you can solve equations by graphing. You can analyze graphs by solving equations. It really solidifies the fact that graphs and doing the algebra are um, two different ways to do the same thing. So let's go on and learn about this here. Okay, given x, find y. So this is where I give you an input. You're given the input, like -3 there. You find the output. So what do? We go to where the x value is -3, and we find where that hits our line. Right there at -1.5. Okay, easy enough. We've done this. This is all the way back in lesson 2, I believe, if you want to go back and refresh yourselves on this. Given x, find y, f of 4, f of 4. So an input of 4, we go to an input of 4, and we find our output is 0.75. Now, in these problems, in this analyzing graph section, sometimes you're going to have to estimate a little bit, estimate. So if your answer was 0.8 or 0.5 or something, or 1 even, as long as you are close and you got the idea, you should be good. Okay, now this is different. Look at this. This is not, we are not given an input value. There is nothing in here. It is f of x equals -1. F of x it means y. F of x means the output. So we are given the output is -1. So on our graph, let's look at where the output is -1, where y is -1, and let's figure out what x values make that true. So instead of given x, find y, here it's given y, find x. So there's the 2 points on our graph. There's one of them. X is -3.5. There's the second one. X is -2. So in these problems here, we're working backwards. We're given the output and we have to find the input. Okay, f of x equals 2. When does the output equal 2? So we put that on our graph there, an output of 2, and we look for what input value gives that output of 2. Well, that's 4.5. Now, you may have been tricked in thinking that there was another one over here. So that open circle on your graph means that this graph goes up, 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 but does not actually get to that circle. It stops right before it. So it stops right before 2. So it does not actually achieve an output value of 2 here. So f of x, the output, does not get to 2 over here. All right, let's keep going on. F of x, or the output, equals 0. So we go ahead and put that line on our graph where the output is 0. Then there's one place where the output is 0. That's at -4 when x equals -4. There's another place where the output is 0. That's when x equals -1. And there's a third place where the output is 0, when x equals 3. Okay, now a question here. We don't have to find the solutions. We just want to think how many different solutions, how many different x values are going to make this true? How many x values are we going to get that give us an output of 0.5? So we want that output of 0.5. Look here, we're going to get one way over there. We're going to get one there right by the axis, or by the origin, one there at around 1.75, and one there close to 4. So we get 4 different solutions, 4 different x values that make that statement true, 4 different x values that give an output of 0.5. Okay, how many x values give an output of -2. So we want to know where our function has an output of -2. So we go to where the output is -2, and our function, oh, it never gets to an output of -2. Look at the output, it's going down, it's at 0, it's negative, it's -1, oh, and then it's turning around. We never get to an output of -2, so there are 0 solutions to that. 0 x values that make that true. Okay, here we go, moving on. Solving the inequalities. All right, now this is where things get tricky. Now it's not just a single point. There's going to be a lot of points that make this true. Let's see why that is the case. We want to know where the function, the output, is less than or equal to 1. Where the output is less than or equal to 1. So there's where the output is equal to 1. Now look here as I trace along with my circle. The output between right here all the way around to over here, all of these outputs are less than 1. I'm at 1 here, I'm going down to an output of 0, to -1, to -2, to -3. All of these outputs are less than 1. So those are good. Those things work because f of x, the output, is less than or equal to 1. As do the parts of the graph over here that are under the output value of 1, under or at the output value of 1, I should say. Now, f of x is less than or equal to 1. We are given the output value. We are given the y value, so we're going to be solving for the x value. So we have to say which x values make this thing true. We have to say which x values give us this green part of the graph. And so if you'll notice, this graph is continuous from here all the way over to here. There's no jumps. As I go along my graph left to right, once I hit this green section, I go all the way to the end of it. So I'm going to put dots there and just translate those dots down to where they are on the number line. And so then I can see, look at where my circle's going. Anywhere from here all the way over to this one, any of those x values make the output less than or equal to 1. They give us these outputs here. Any of these x values coming in blue here. When x is -5, the output's down here. When x is -4, the output's down here. When x is 3.5, the output's here. When x is, or -3.5. When x is -3.2, the output's right here. All of these outputs are less than or equal to 1. So all of these x values make this statement down here, f of x is less than or equal to -1, true. Same thing goes for over here. When x is 0, the output's at -2. When x is 0.5, the output's down here at -1.5. When x is 1, the output's at -1. All of these outputs for these x values are less than or equal to 1. So all of these x values are solutions. Now, how can we say all of these x values from here to here and all of these x values from here over to here? Well, those are two intervals, so we're going to use interval notation here. So this first one, we always go left to right with our interval notation, smallest to biggest, goes from -7 to 3, or to -3, sorry. And I include with brackets both of the endpoints, because at both of those endpoints, at -7, what is f of x? At -7, f of x is 1. And that works because my output, or f of x, just has to be less than or equal to 1. And so 1 works there. So I go from -7 to -3. That's one set of x values that work. And then union, and I add my other set of x values from -1 all the way up to 3. Okay, so this is just the set of x values that make this true. All right, let's look at another one. Solve for the x values. The f of x is greater than 1. So let's look on our graph where this thing is greater than 1. The same first step we would do if we were trying to solve when f of x equals 1. But now we highlight all of our parts where the function, the output, is greater than 1. The output here is 2, then 3, then 4, then 5. The output here goes from 1.2, 1.5 up to 2, and then back down. All of these outputs are greater than 1. So we need to get the x values that make these true. Now, think about right here, what's going on, right above my, or under my circle. At an x value of 3, the output is 1. The output is 1. So does the x value of 3 make this true? No, because it gives us an output of 1, and 1 is not greater than 1. So that's why for this problem, we're going to put the open circles here wherever we get to 1, because our problem said find where the output values are greater than 1. And at those points right there, the output values are not greater than 1. Okay, so I'm going to drop those points straight down to my number line because I want to figure out which x values work. Now, if we look over here, any x value in between here and here, yep, those are all these points right here. They give us all these outputs. An x value right here where my spinny circle is goes straight up to this output. It gives us this output, which is greater than 1. So all of those x values work. That's why that gets highlighted. Okay, over here, if I'm at this x value where my spinny circle is, I get this output. If I'm at 2, I get this output. If I'm at 2.2, I get this output. All of those are greater than 1. So all of those x values make this true. They make f of x greater than 1. And now finally, if I pick any x value here, after 3, going on forever and forever, they give me an output greater than 1. So the final thing I have to do is change this into interval notation. So this first one, I can include this endpoint right here at negative 7.5 because it has an output, defined output, a filled in circle up here that is greater than 1. So negative 7.5 up to 7. I don't include, or negative 7.5 up to negative 7. I don't include negative 7 because at negative 7, my output is 1. And if my output is 1, then this is not true anymore. And then I jump over here. And then immediately after negative 3, so a parenthesis, so I don't include negative 3, but immediately afterwards, x values all the way up to, but not including negative 1, all of those give me outputs greater than 1. And then I jump over here. Now any x value immediately after 3 going on forever and forever. So all the way to infinity. Now, you do not need to write this plus sign in front of the infinity. Just leave infinity as infinity. It's just like if you're going to write 7, you don't write plus 7 to tell someone that it's a positive 7. If you want to say negative 7, you put a negative in front of it. So if you want to say negative infinity, yes, please put a negative in front of it. But if you're just saying normal, good old positive infinity, you don't need the plus sign. All right, that's the end of these notes, I believe. Yep. So hope that helped, and have a good rest of your day.